So we're going to continue our discussion of pH here. And before we get into titrations, I want to talk briefly about how we would determine pH. Because in order to be able to actually do any sort of titration, you need a method that will let you figure out or let you accurately determine what is the current pH of my solution. So there's two common ways that we do this. The first is to use what's known as a pH meter. A pH meter is something that we calibrate using buffer solutions at known pHs. Basically, you put your pH meter into a couple different solutions. Usually you use 4, 7, and 10, and you put it in the pH 4 solution. You tell the meter this is pH 4, you do 7 and 10, and that's how you know your meter is calibrated. But these use what are known as electrochemical methods to determine pH. And electrochemical, that type of topic, is something that we get into in our final chapter, chapter 14 in this course. And pH meters can go from, very, very simple pH meters to, very complex and very sophisticated. And just to show you a couple of examples. So here's a very simple example of a pH meter. In fact, pH meters like this, that are this simple, you can actually buy, even on Amazon. They're meant for use at home if you want to test, for example, a swimming pool. And they run about $15. Not the most sophisticated or the most accurate, but they work pretty well for most things. On the other hand, we also have pH meters that are much more complex, such as this one. These are actually the ones that we have in the lab, and they do a lot more things and, pretty fancy, but comes at a price. The cheap pH meters, you could probably buy 30 or 40 of them for what one of these costs. So it all depends on your needs as well as how accurate you want it to be. You can see already one of the differences. This one gives you extra decimal places. Much easier to calibrate. And then when you get into some of these menus, a lot more options with a pH meter like this. Now, we don't always need to be this accurate. Sometimes we just need more of a vague idea of what the pH is. And so we use what's known as an indicator. So indicators are dyes that change color at different pHs. One of the neatest examples of a dye is you can actually use red cabbage. And you can actually use red cabbage to make an indicator solution that goes through a whole range of different colors depending on the pH. And it's not terribly difficult to make either. So you can see here exactly what you can do. So you take a bunch of red cabbage, you chop it up. Don't even have to do a good job chopping it, just chop it up roughly. Throw it in a bunch of water, boil it for a few minutes, strain out the solid, and the liquid that's left behind you can use it as an indicator. And you can see to the right that the color changes depending on what the pH is. So if you have a strongly acidic solution, 0, 1, 2, you'll get a nice bright red color. As you get closer to neutral, it starts going more purple and over to blue when it's completely neutral. And then as you get into basic solutions, it goes green and finally yellow. Now, we don't always need an indicator that's this complex or it gives us this much information. And so more commonly, we use things like phenolphthalein. Phenolphthalein, if you're between a pH of 0 and 8.2, it's completely colorless. When you go from about 8.2 to 12, it turns pink. And when you get to a pH greater than 12, it becomes colorless again. But the reason this is useful to us is this number right here, 8.2. At 8.2, that kind of pH, that's just above the point where our solution would be neutral. And so if you think about what's going on in a titration, we have a bunch of, we have a solution of base, and we start adding acid into that. No, I'm sorry, let's get this correct. We have a solution of acid, and typically we start adding base to that. So what happens is our pH and we can actually plot that pH versus the volume of base. So as we start adding the base, pH goes up gradually. As we get nearer what we call the end point, it goes up very quickly, and then it starts to increase slowly again. The point that we're interested in is around here, when we have equal moles of acid and base. Well, typically, not always, but typically that comes with a pH of around 7. And so given that this changes color when it hits a pH of 8, basically what we do is we add base to our acid solution here, and when it changes to pink, that's when we know our titration is done. Now there's many other indicators out there as well, and just as an example, there's one called methyl orange, and it gives us different pHs. So if methyl orange is added, if our pH is less than 3.1, the solution is red. If it's greater than 4.4, it's orange. And if it's between 3.1 and 4.4, then the solution is colorless. And there's many other indicators out there that have other pH ranges as well. So you can actually use many different indicators, and you could eventually narrow down the pH of your solution to a very, very small range. Now, why do we do any of this? Well, we do this for the purpose of acid-base titrations. In an acid-base titration, we use a solution of known concentration that we have first standardized. What do we mean by standardized? By standardized, we mean that we've accurately determined its concentration. Typically by using a titration with a acid or base that we've actually weighed out by mass, because that's typically our most accurate method. So we use a solution of known concentration that we've standardized in order to determine the concentration of an unknown solution. And again, typically we use an indicator to determine the endpoint. The endpoint is the point where we end the titration. Now, because of the way these indicators work, for example, phenolphthalein doesn't change color until it gets to about 8.2. Sometimes we have to account for what we call titration error, which is the difference between the endpoint being the point where we stop the titration, and the equivalence point. The equivalence point being the point when equal moles of acid and base are added. Now, how significant is this error? Does it really matter? And so we're now going to look at a set of calculations that deal with a strong acid, strong base titration, which is the most common type of titration that we would do, and see if this type of titration error matters. And again, this error stems from, let's say, the equivalence point of a strong acid, strong base titration is around a pH of 7. Well, remember, phenolphthalein gives us an endpoint at 8.2. So that's where this error is coming from. The fact that we might have a equivalence point around 7, but an endpoint of 8.2. So let's go through a problem here and see how this works and see how big of an error this is and how much we should be concerned by it. So we have HCl plus NaOH gives us sodium chloride and water. So in this case, I'm going to give you both the concentration of the acid and the base because we want to look at the pHs. So we have 50 milliliters of 0.1 molar HCl. And we're going to use 0.1 molar NaOH. So I want to calculate the pH of this solution at certain times. 25 milliliters of NaOH. 49 milliliters of NaOH. 49.90 milliliters of NaOH. 50.10 milliliters of NaOH. And 75 milliliters of NaOH. So recall our equivalence point comes at 50 milliliters of NaOH. Our endpoint comes at pH of 8.2. So let's now see if this matters. Now the reason we start with we do a strong acid, strong base titration is we can make the assumption that everything we add is going to react. Now, what we're going to do is we need to know moles for every one of these calculations. Now, the moles of acid are not going to change, so that's a calculation we can do one time and leave it. So 50 milliliters is 0.05 liters. If we multiply that by its concentration of 0.1 molar, we find we have 5 times 10 to the minus third moles of HCl. And that's going to be the same for every one of these calculations that we do. All right, now at 25 milliliters of sodium hydroxide, we're going to need to know how many moles we have. So 25 milliliters is 0.025 liters times the molarity of 0.1 molar means we have 2.5 times 10 to the minus third moles of NaOH. So we could think of this right now as a limiting reactant question. HCl plus NaOH. So we have 5 times 10 to the minus third moles of HCl 2.5 times 10 to the minus third moles of NaOH. I don't really care about the products. They won't affect anything that we're doing. So which one is limiting? Well, the limiting reagent is going to be the one that we have less of, and that's the sodium hydroxide. So how much of the sodium hydroxide reacts? All of it. How much HCl is left? Well, given that it's a 1-to-1 ratio between hydrochloric acid and sodium hydroxide, the amount of sodium hydroxide we have will be the amount of HCl that reacts. And so we're left with 2.5 times 10 to the minus third moles. Now, we need to calculate the molarity, because if we're taking pH, we need concentration. So the concentration of HCl, or more importantly, the concentration of H+, these are equivalent, if you recall the practice we did previously. The concentration of H+ is equal to the number of moles, 2.5 times 10 to the minus third moles. But what's the volume now? Is it still 50 milliliters? The answer is no. Why not? Well, we started with 50 milliliters, but then we added another 25 milliliters of solution. So we now have a total of 75 milliliters. And we can convert 75 milliliters into liters. And we get 0.033 molar. Finally, the pH is equal to the negative log of that, or 1.48. All right, so I'm going to go back to that final slide, and we're just going to start keeping track of these. So 25 milliliters, this is going to be our amount of NaOH added. We get a pH of 1.48. Now, we never did a 0 point, but we could have done that very easily. We started with 0.1 molar HCl, so it would just be the negative log of 0.1, or 1. All right, so let's keep going. Now, I'm not going to go as careful through each step in each of these next situations, because we're really doing the same thing over and over again. So our 49 milliliters of NaOH now, we could calculate that out to 4.90 times 10 to the minus third moles. Now that's still less than the amount of HCl we had, which is 5 times 10 to the minus third moles. So the excess of HCl is equal to 5 times 10 to the minus third minus 4.90 times 10 to the minus third, or 1 times 10 to the minus fourth moles. Again, we can calculate our concentration of H+ is 1 times 10 to the minus 4 moles. But now we've added 49 milliliters. We add that to our original 50, so we have 99 milliliters, or 0.099 liters. Gives us a concentration of 1 times 10 to the minus third molar, or a pH of 3. So again, that's after we added 49 milliliters. We now have a pH of 3. All right, at 49.90 milliliters. That corresponds to 4.99 times 10 to the minus third moles of sodium hydroxide. So we're getting even closer to the amount of HCl, but we still have an excess of HCl. How much of an excess? Well, again, the amount of HCl doesn't change. 5 times 10 to the minus third moles minus 4.99, the amount of sodium hydroxide, times 10 to the minus third. Again, remember, we're assuming because this is a strong acid reacting with a strong base, that all of the one that we have less of will react. So our excess of HCl here is 1 times 10 to the minus 5 moles. We can now calculate our concentration of H plus as being that excess number of moles divided by the new volume, which is 99.9 milliliters now. And we get 1 times 10 to the minus 4 molar. pH is the negative log of that. Or 4. So 49.9 milliliters pH of 4. Alright, now we're finally going to cross over to a point where we have more base than acid. We're at 50.10 milliliters, or 5.01 times 10 to the minus third moles of sodium hydroxide. Now, because we have an excess of base, we have more base than acid, we no longer calculate excess HCl, we now calculate excess sodium hydroxide. And so that's equal to the amount of sodium hydroxide minus the amount of HCl. So now we have an excess of sodium hydroxide, which is 1 times 10 to the minus 5 moles. Again, as we did with HCl, we can calculate the concentration of the hydroxide as being the excess number of moles divided by the volume. That volume is now 100.1 milliliters because we've added 50.1 milliliters to the original 50. And so the concentration of hydroxide is 1 times 10 to the minus 4 molar. We can use this to easily calculate the pOH as the negative log of 1 times 10 to the minus 4 molar. That's equal to 4. And the pH is the pOH minus, no it's not, pH is 14 minus pOH, or 14 minus 4, or a pH of 10. Finally, we can do 75 milliliters. This will calculate to 7.50 times 10 to the minus third moles, which means we now have a much larger excess of hydroxide. 7.50 times 10 to the minus third moles minus our amount of HCl, 5 times 10 to the minus third moles, or an excess of 2.50 times 10 to the minus third moles. As before, we can calculate the concentration of hydroxide. Over the new volume. We get 0.02 molar hydroxide. We can calculate the pOH as the negative log of 0.02 molar. We get 2. And therefore the pH is 14 minus 2, or 12. So what we find here is that most of our pH change occurs in a very, very small range. You can see as we went from 0 to 49 milliliters, the pH only went from 1 to 3. And same thing as we went from 50.1 up to 75, we only went from 10 to 12. But in that range of 49.9 to 50.1, we went from a pH of 4 to 10. And so if you think about, do we get a big error here between the endpoint and the equivalence point? Well, where would the 8.2 pH show up? Well, somewhere between 49.9 and 50.1. Probably a little bit above 50, maybe 50.03, 50.04. But you can see the difference in that equivalence point and the endpoint is exceptionally small. And so outside of very unusual situations or situations where we need extraordinarily accurate titrations, in most cases the titration error is pretty negligible, and we see that here. Alright, now before I send you off to do some practice problems, I want to go through a couple more problems that are more the type that we would typically deal with when we do a titration. So let's say that we have 25 milliliters of 3 molar sodium hydroxide. And to reach the endpoint, we need 19.6 milliliters of HCl. So what is the concentration of the HCl? Well, in a question like this, one of the things that makes a big difference is whether or not the moles are equal. Or in other words, does 1 mole of sodium hydroxide react with 1 mole of HCl? If it does, then we can use an equation we've seen before. And again, it's because the moles are equivalent. So the molarity of the first solution times the volume of the first solution is equal to the molarity of the second solution times the volume of the second solution. And again, we can do this if acid and base react in a 1-to-1 ratio. If they don't, then you have to account for that in the stoichiometry. So if our first solution is our sodium hydroxide, that's 3 molar times 25 milliliters is equal to the second concentration, the HCl, which we don't know, times its volume of 19.6. All we have to do is solve for M2, and we get M2, or the HCl solution, is 3.8 molar. So that's how a titration works. And as you can see, the calculations are typically very, very straightforward. They're just another application of M1V1 equals M2V2. Again, the reason for that is because as long as we have a 1-to-1 ratio of acid and base, then the number of moles are equal, and we don't really need to worry about anything else. So the last thing I want to say before I give you some practice to do is when we do a titration in the lab, one of the things we usually do is we do the titration 2, 3, 4, 5 times. The reason that we do that is we want to make sure that we get an accurate titration. And so typically when we do that kind of titration, we do it over and over again until we get results that are consistent and are similar. And so if we start getting results that aren't similar, in those cases, then we throw out any numbers that are way off. So at this point, you should start working on in-class exercise number 21, which deals with some calculations that relate to titrations.